I mean, it'll get easy. You don't have to grade all that.
All right, 7-7. Here we go. Okay, so 7-7 talks about polar form of complex numbers. So we're seeing that polar piece from the last section come in, and then we'll get to the theorem towards the end here. Okay, so first thing we need to talk about is the physical representation of a complex number on a graph. So we probably haven't graphed complex numbers before now because we have a real axis and an imaginary axis. Normally we have an x-axis and a y-axis when we plot planes. We think of a complex number, we represent a complex number, a plus bi. We call a the real part, it doesn't have our I, and we call b the imaginary part, it does have our I. The real axis is where you're going to plot a, and the imaginary axis is where you're going to plot b. So you can almost think of this like a coordinate, okay? So the real part is the first part, your horizontal component. The imaginary part is your vertical component. So if I plotted a plus bi, I would go a left to right, I would go b up or down. That would be where that complex number is located. So the first thing we're going to do at the bottom here is just practice plotting complex numbers. So the first complex number is 2 plus 3i. So positive 2 takes me 2 to the right on the real axis. 3i moves me up 3 on the imaginary axis. So it's going to be in quadrant 1. 2 plus 3i. I'll just label them. Okay. So how would I graph negative 3 plus 2i? Left 3, up 2. Okay. How would I graph 4 on this axis? Just 4 to the right. So if you just have a real number, it's on the real axis. Or if you just have an I term, it's going to be on the imaginary axis. Like you can see negative 2i's graph there. Negative 2 minus 3i is going to place me in what quadrant? Quadrant 3. Negative 2 minus 3i. And then 3 minus 2i is going to end up in quadrant 4. 3 to the right, 2 down. Okay, makes sense? Any questions with that? Quick little slide. Okay, next, a definition. So this is now going to look more like what we've been talking about with vectors and polar coordinates. It's the absolute value of a complex number. This is also called, instead of absolute value, you might see the word magnitude or modulus. It all means the same thing. And the absolute value is this wonderful formula little right here. When we talk about an absolute value of a number, we talk about its distance to 0. Well, we don't have a number line anymore. We have this real imaginary axis when we graph these. So what we'll do is we calculate that hypotenuse that looks like in this triangle. Okay, so A, my real part left and right, B, my imaginary part up and down. If I want to calculate the distance to 0, which is the absolute value or the magnitude, it ends up being that little Pythagorean theorem again. So we've again seen this formula come up one more time. We did magnitude of vectors with this. We calculated the r value with our polar coordinates with this formula, and now it's popping up again when we're doing the absolute value of our complex numbers. Just the first component squared plus the second component squared under a radical. So finding the absolute value of this number, negative 5 plus 12i, I would do the square root of negative 5 squared plus 12 squared. So negative 5 squared gives me 25. 12 squared gives me 144, which is the square root of 169, which is equal to 13. So we're just getting a single number here. It should not be an imaginary number. It's going to be a real number, and it represents that distance to the origin when we plot that point. Okay. Now this also works for just real numbers. If I see negative 7, you can think of that as negative 7 plus 0i if I write it in that complex form. So that would look like negative 7 squared plus 0 squared, which would be a 49. And then the square root of 49 gives me 7, which we know the absolute value of negative 7 is 7, but you can see that this formula works for any type of number now, not just our real numbers, okay? It also works if you just have an imaginary number. This, again, probably not one you want to use a formula for. If you imagine graphing I, it's just going to be 1 unit up on that imaginary axis. So the distance to the origin is 1, but you can see that with the formula if you want. You can think of this as 0 plus 1i if I wrote it in that complex form. So that'd be 0 squared and 1 squared, which is the square root of 1, which is 1. Okay, so if we're on one of the axes, we can just count that distance. If we're in the middle of one of the quadrants, like that first one, it's a little better to use the formula. Okay. What's wrong? Okay. Questions calculating the absolute value of a complex number. Distance to 0. Moving on. All right. Polar form of complex number. So right now this is going to be like kind of a fun thing we can do with complex numbers, but you're going to see in a few minutes it's going to make certain calculations with complex numbers easier. So we have 4 conversion formulas. Let's say we have this complex number, a plus bi. So a again is that real part and b is the imaginary part. Its polar form looks like this. R times the cosine of theta plus I sine theta. You might see theta referred to as the argument. Okay, it just means it's the angle of rotation, that direction angle. We've seen that before. So this polar form, that looks like, if you guys remember what we used for vectors, we had the magnitude out front of the parentheses, and we had cosine theta I plus sine theta j, where I and j were those unit vectors. It's a similar form again here, where cosine comes first and sine comes second. That's our horizontal and our vertical components. The formulas below, these are the same formulas that we were using in the last section, but instead of an x and a y, we have an a and a b. Okay, but same formulas as before. So my a goes with my cosine, my b goes with my sine. To find r, we do our Pythagorean theorem, and to do tangent, we do the y over the x, or in this case, the b over the a. So even though it looks like new formulas, it's just a new context we're applying them to when we do this. All right, so at the bottom, let's say I want to write -1 minus I in polar form. So you first need to know what a and b are. What's a? -1, and what's b? Both are -1 here. It's just the number in front of the I for that b. Okay, you need an r and a theta to get your complex form, to get your polar form. So to get r, it's just the first component squared plus the second component squared. R is that absolute value. It's that magnitude. So what am I going to get under that radical? Rad 2. Okay. To get theta, just like in the last section, we're going to use our tangent formula. Tangent equals y over x, or in terms of complex numbers, b over a, -1 over -1. So it equals 1. It doesn't say if we want a degree or radian here. Let's do degrees, that's fine. Can you give me 2 places on my unit circle where tangent is equal to 1 in degrees? 45 and 225. And just like our polar points, one of these is right and one of them is wrong. If you graphed the complex number -1 minus I, like we did on that first page, what quadrant would that be in? That would be in quadrant 3. So which of these angles am I going to choose? 225. Okay, so I have my r, I have my theta, my polar form of z. Another way to write this complex number is the square root of 2 times the cosine of 225 plus I sine 225. If you simplify further, if you take the cosine and the sine from your unit circle and you distribute the rad 2, you go right back where you started. So simplifying this is the check. You can take you back to the original problem. Okay? You guys try the next one. I'll give you a minute. Find the polar form of this complex number. All right. Let's check it. Did you get 2 for r and 60 for theta? 2 cosine 60 plus I sine 60 is our polar form. And then again, if you want to check it, you just evaluate. Find the sine and the cosine, distribute your 2 through, you're right back where you started. Any questions on that? Okay. The next slide is just kind of showing you that check. So here we have, and we're just going to do one of these because they're quick. Here we have that polar form. It's a radian here, but you can see that the r is out front. So in that first one, r is 2, and my theta is next to my angle there, or next to my sine and cosine is my angle, pi over 6. We want to write this in rectangular form. So rectangular form means put it back to our normal form, our a plus bi, when we're talking about complex numbers. So this is really just simplifying completely. Okay. So can you tell me what the cosine of pi over 6 is? Plus I times the sine of pi over 6, 1/2. And if I distribute 2 through, what's going to happen there? 2's are going to cancel. So rad 3 plus, you could say 1i, we usually just say I. And that's it. That's rectangular form. So if you're asked for something in rectangular form, you just want to simplify all the way. If it asks for polar form, you can stop as soon as you have that r and theta. So you just want to read those instructions carefully when you're doing your homework. Okay, so we won't do the other one. Same thing, just simplify it. Questions on that? Okay, next. So now that we can put something in polar form, we can do some different calculations with it. The first set of calculations we can do is we can find the product, so multiply, and the quotient, divide complex numbers. We have done this before. Well, maybe not us in particular, but you guys have. Like if I say I multiply complex numbers, you've done stuff like this before, right? Where you FOIL it out and simplify. We might have done 1 or 2 problems where that happened at some point this year. And you've divided too, like this. Dividing is a little more complicated because when you divide, the I is a square root of -1. It's a radical in the denominator. You need a conjugate to be able to do that. So this was something that took a little bit more work when you guys did that in the past. Dividing is very easy if you can write your complex numbers in polar form. So the 2 formulas that you need, let's say you've got Z1, it's the first complex number that you're using, and it's in its polar form. So R1 and theta1 are its components. And then Z2 has R2 and theta2, whatever that angle and magnitude are. Here's how we find the multiplication, the product, and the quotient of those 2 numbers. So if I want to multiply, I multiply the r's together first. This form, if you guys look at it, is the same as the form we were just using a second ago. It's cosine of an angle plus I sine of the angle. We just add the 2 angles we have together to get that angle. If you're dividing, it's very similar. Instead of multiplying the r's we have, we divide the r's we have. And instead of adding the angles we have, we subtract the angles we have. And that gives us the new angle that we're looking for, and that gives us whatever the product or the quotient is. And you can then simplify it, put it back in rectangular form if you need to. All right, so we're going to do that with this set of problems at the bottom. So we've got complex number Z1, its magnitude is 5, and its argument, its angle is 75 degrees. Z2 is 2 and 60 degrees. We're going to start by finding the product, Z1 times Z2. Okay. So to do that, the first thing I need to do are multiply my r's together. My r's are 5 and 2, so if I multiply those together, I get 10. And then we add our angles together. So 75 and 60 gives me 135. And that is the product of those 2 complex numbers. It says leave the answers in polar form. If it said to put the answer in rectangular form, you would just simplify further. Find the cosine and sine off of your unit circle and distribute the 10. If you divide the complex numbers, you divide the r's out front. Now, division and subtraction order matters, so make sure that Z1 and its components always come first, Z2 and its components always come second. Divide the r's, that would be a 5 over 2. And then we subtract our angles inside the cosine and the sine. So here, 75 minus 60 would give me 15. And problems like this, where if we did want to put that in rectangular form, that second one would be a lot more complicated because 15 degrees, we can find the cosine and the sine of it, but we have to use trig identities to do that. We know how to do that. It's just really involved. So a lot of times if we get kind of weird angles like that, we just say, just leave it in polar form. It's not worth all the simplifying. Okay. Questions, multiplying or dividing complex numbers in polar form? Okay. All right. So let's use that property then of multiplying. So let's say I've got this complex number z. It has its r value r and its argument theta, whatever those are. I want to find z squared. I want to square a complex number. So I'm going to think of that as z times z. Okay? Which means I can use my multiplication property that we just did. To multiply z times itself, I start by multiplying the r's together. R times r gives me r squared. And then inside the parentheses, I'm going to have cosine of an angle plus I sine of an angle. It's always the form I use. And to get that angle, if I'm multiplying my complex numbers, I add the thetas together. So if I have theta and I add those together, I get what? 2 theta. So any complex number squared can be written like this. If you can find the r and theta, it's r squared cosine 2 theta plus I sine 2 theta. Okay, let's do the same thing for z to the third. What can I multiply together to get z to the third? Z squared and z, and I have both of those. Okay. Z squared and z, multiply their r's together first. So that would be r squared and r. Multiply those together, you get r to the third. And then again, it's going to be cosine theta plus I sine theta. To get that theta, again, I add the thetas I have. I have a 1 theta and a 2 theta. If I add those together, I get 3 theta. Okay, so you've got z to the first, z to the second, z to the third. Are we seeing a pattern yet? If I said find z to the nth power, what would that be? You are as smart as Moivre. That's his theorem right there. Okay, so he figured out if I can multiply them, I can find all these powers, and I'm going to get that same thing, that same format over and over again. So this is Moivre, if I can spell it right. I'm pretty sure that's on the next slide. Okay, so that's what we use this for. If I say find z to the 110th power, that's not hard, because as long as I can find r and theta, I can multiply or take to 110th power. But if I gave you a rectangular form complex number, like if I said -3 plus 4i and take that to the 110th power, that's a problem, because that is foiling 110 times. So this is really why we have complex numbers in polar form, because this is not fun if I leave it like this. But if I write it in polar form, I can use this nice little pretty formula, and I can take it to very high powers if I want to, and get a very pretty answer and save myself a lot of work. Okay? All right, so let's do that, shall we? We'll do one together, and you can try one on your own. All right, so there's a theorem. We're going to use z equals -1 plus I is going to be our complex number, and we're going to take it to the 8th power, and it also works for negative powers. We're going to take it to the -12th power. As long as it's an integer n, it works. All right, so if z is -1 plus I, can you tell me what a and b are? A is -1, b is 1. Okay, in order to use this formula, I need 3 pieces of information. I need n. What's n? 8. I need r. I don't have it. How do I get it? Magnitude. Pythagorean theorem. Square root. -1 squared plus 1 squared. What does that give me? Rad 2. And I need theta. How do I get theta? Tangent? Tangent's equal to what? Flip it. I mean, here it doesn't really make a difference, but it's always the b over the a. Okay, so what quadrant is this angle in, by the way? Or this angle, this complex number? -1 plus I. Where would that be plotted at? That'd be in quadrant 2. So that kind of tells you what angle you're looking for. We're looking for an angle in quadrant 2. What angle in quadrant 2 has a tangent of -1? And you can use degrees, it's fine. Boop. My internet went out. See, mine did it too, Brody. $135 is right. Let's see if that wants to. There we go. It reconnected. Okay. 135. Good. Okay, so we have n, r, theta. Now, de Moivre's theorem. If I want to take z to the 8th power, so I'm taking -1 plus I, that complex number, to the 8th power. I'm going to do r square root 2 to the 8th. Cosine n is 8. Theta is 135 plus I sine, that same thing, 8 times 135. You can use your calculator for this. Square root 2 squared is 2. And then if you do that to the 4th power, that's equivalent to rad 2 to the 8th, which is going to be, I believe, 16. Let me double check myself. It's still early this morning. Rad 2 to the 8th. 16. Okay. And then we can multiply 8 times 135, which would be 1080. This is the answer in polar form. If the question said, leave your answer in polar form, you're done. This question says, put it in rectangular form. So we need to simplify a little bit. So this is just unit circle stuff now. 1080 is too big for our unit circle. So what do we do if it's too big for our unit circle? Subtract, and you're going to have to subtract a few times. 1080 minus 360 is 720. Minus 360 again is 360, or you could take it even further and make it a 0. 360 or 0 would be something we can deal with. What is the cosine of 0? What is the sine of 0? So I have 16 plus 0i, if I distribute that 16 through, or we're just going to say 16, probably. So if you take -1 plus I, that complex number, to the 8th power, if you were to FOIL it out 8 times, your answer would be 16. Everything would cancel. Right? And this is a whole lot easier than doing that foiling. All right, you guys try it to the -12th power. So you've already got the n, the r, the theta. You can reuse those for this next one. Well, you can reuse r and theta, I guess, at least. Your n's going to change. It's not a negative. There's no line there. 1/64. No, it is negative. It is negative. Just kidding. Sorry. Second guess myself there for a second. Both of these work out that the I term is gone, that it just ends up with a real number. That doesn't happen every time. It's just this value that we're dealing with. So if there's a I left or if there's a radical left, that's fine. Okay? Any questions on this? All right, I just got one more problem for you and we're done. So, a version of de Moivre's theorem is his nth root theorem. So his theorem says, let's take it to this integer power. A root is a square root, a cube root, a fourth root. That's not an integer. It's like a 1/2 power, a 1/3 power, a 1/4 power. That's what this formula does. So you're going to see a lot of similarities here. So let's say I want to take z, my complex number, to a square root or a cube root. That's what I'm calculating. So I'm doing a 1/n power. So if it's a square root, it would be 1/2. If it's a cube root, it would be 1 over 3. If it's fourth root, 1 over 4, so on and so forth. Theta and n are still those values that we've been using. R is still the same value. K is the only new guy that shows up in this formula. K is multiple values. If you have a square root, there are 2 of them. If you have a cube root, there are 3 of them. If you have a fourth root, there are 4 of them. So you have to use the formula multiple times. K, when you use the formula, will be used as a value of 0 all the way up to 1 less than your n value. So if I was going to do square roots, my K would be 0 and 1. If I were going to do cube roots, it would be 0, 1, and 2. I would have to use 3 of them. Does that make sense? If I was finding fifth roots, my K's would be 0, 1, 2, 3, and 4. All the integers starting at 0, leading up to 1 less than my n value. So I'm going to show you what that looks like with this problem here. So this one says, find the 3 cube roots of negative 1 plus I, and we're going to leave our answer in polar form. The argument, the angle, is going to be in degrees. Negative 1 plus I is the complex number that we just used in the previous problem, and I did that intentionally just to save us a little bit of time. So R we had, that was square root of 2 from the previous problem, and theta from the previous problem was 135. If you didn't have those, you'd have to find those first, okay? All right, so using the formula, if it's a cube root, I'm going to have 3 values of K. K is 0, K is 1, and K is 2. Plugging it in, starting with K is 0. I'm going to take my R, square root 2, to the 1/3 power, because I'm doing a cube root. N is 3. Cosine. My theta, 135, plus 360 times K is 0 over 3. Plus I sine, all the same stuff. 135 plus 360 times 0 over 3. All right, square root 2 is the same as 2 to the 1/2 power. To the 1/3 power, if you do the 1/2 times the 1/3, it's just 2 to the 1/6, or you could say the 6th root of 2, same thing. Then I need to figure out what that angle is. You can use your calculator for this. Do the 135 plus 360 times 0, that's just 0. So 135 divided by 3 is going to give me 45. Plus I sine 45, and that is your first cube root in polar form, argument in degrees. The only thing that's going to change for the next 2 problems is the K value. So now I'm still going to have a rad 2 to the 1/3 power, but in this one, my K is 1. Over 3 plus I sine 135 plus 360 times 1 over 3. Okay, so it's still going to be 2 to the 1/6 out front. Again, the only thing that's changing is that angle. 135 plus 360 times 1 divided by 3 gives me 165 plus I sine 165. Okay, and I'll save you work on the third one. The third one, you end up with an angle when you make K equal to 2 of 285. So my angles, that number out front stayed the same throughout. The angles are the only difference. 45, 165, 285. Do you guys see a pattern there? They're plus what? 120. Wouldn't it be nice to just know I was going to add 120 degrees on each time after I found that first one? How are 120 and 3 related? Maybe? Can we find a relationship there with something special that we use a lot? $120 times 3 is 360. That's pretty special, right? Our full rotations. If you do 360 divided by n. That's what you add after you get the first one. So if I said find the fifth roots, there's 5 of them, that's a lot of work. Just find the first one and then keep adding on whatever 360 divided by 5 is. And that'll give you all the other ones. Shortcut. I just told you. I had to show you at least one. I didn't make you do that much work. I felt like I was pretty nice there. And we're done with 7-7. That's it. All of it. All right, so I'll do cell phone lotto. Tomorrow is a work day. 7-6 Math XL is due tomorrow night. 7-7 Math XL is due Sunday night. Those are your last 2 Math XLs. That's it. There are no more Math XLs after this weekend. All right.